In order to complete the first task of the file design activity, create a program that asks the user for the percentage they achieved in the exam and store it in a file with today's date and time. This is what you should have built. This is a very simple implementation. Initially, I've imported from the date-time library, so I can use that automatically. I've used a blank array, and I've got a try and except construct to see if there's already a results.txt file there, and if it is, to read it into memory and replace this blank array with it. And if not, just to tell me there's nothing there. So I've got some subroutines there, but let's go on to the main body of my program. I've got a while true loop, which is a forced infinite loop, and I'm asking for the score, turning it into an integer. I'm taking the date from the datetime function and setting it up so that I get day, month, year, hour, minute, seconds. I'm then creating a row for it, so it's another one-dimensional array that has a score and the date in it, and I'm appending that to my results table. That gives me a 2D array where my first column is score and my second column is date. I'm then going to print that out. And then at the end of the loop, I'm going to go and save that. The print function is just a very simple subroutine that prints it out with a heading. Let's see that execute and see how that works. So my percentage achieved, I was very good and got 99% in this exam, and you can see added it to the file. Next exam I got 80%, and it adds it to the file. You can see they're just being added at the end. The sequential file activity uses pretty much the same code that we used before, but with one added extra. I've added some simple code to sort the array. Now, because I picked the score as the first column, the sorted command always sorts on the first column. So what this will do is it will sort our array every time it adds to it, before going about the same work. So if I run the data here already, and I'm going to add a percentage of 1%, which hopefully will end up at the top of that list, there we go. I'm then going to add a 99%, which should end up at the bottom of the list. And there you go. This is an indexed file now, isn't it? We're indexing it based on the percentage scored. So trying to find a record of when a certain percentage was scored would be significantly easier. Building the hash function is a reasonably complex program, and we'll talk about that in a second, but let's check it works. If I add an item to it using the simple command line menu, it'll ask me to enter my string. I'm going to just do test. So it's stored at indication 0. Let's use show to see that. There we go. Let's add another one. Let's add computer science. So that's hashed at 9. And let's see that in there. Fantastic. So if I find and I look for something that is in there, like test, there we go. So test was found in index 0. So we can also reset the hash table quite simply here by typing in reset, which should, if I click show me the entire hash table. So let's go through that programming code and see what we've done. First of all, I brought in two libraries that are quite useful, time and OS. These allow me to pause and to manipulate the way that this part of the screen looks. And then creating a hash table, which is a one-dimensional array with 16 blank rows. Now, the way in which we do that in Python is we use the command none, which gives a blank row. So it sets aside some memory for it, but doesn't put anything in there. So let's go down to our main program at the bottom. We've got an infinite while loop here, and we're starting with the menu system. So asking whether we want to add, find, reset, or show. And I'm doing that by slicing out the first letter, lowercasing it, and looking for A, F, R, or anything else. A will do an add hash function. F will do the find hash function. The R will reset the hash table to 16 blank rows, tell us that, pause it, and clear the screen. And anything else will print out the hash table, leave it on the screen for 2 seconds, and then clear. Let's come have a look at some of these subroutines. The print hash table is full of commands just to print things out in different colors. So it prints out different parts of it in different colors, and making sure that we're printing out numbers to 2 decimal places and things like that. So it's a reasonably simple set of loops that go through and print out the contents of the hash table, of course using the global command so that I can access and manipulate that. The add hash function, again with a global command to access and manipulate it, asks for the word they want to enter, lowercases it, starts with the hash value of 0 and uses a for loop to iterate through each character, checks to make sure the character is a letter, and then adds the value. Now I used the odd or ordinal function to get the ASCII value of the character and took away 96 because the first lowercase letter is 97. So A lowercase is 97. So I've taken away 96 so that A becomes 1. I'm then moduloing that by 16 to work out where it's going. Then we have a loop to actually try and add it. So I've got a Boolean value there to see if it's added or not. And that just checks to make sure that I can add it. So I don't need the overflow file. I'm going to use a loop to go through all data locations from 0 to 16. And we're going to try to stick it in the place where it's supposed to be. We set our starting position to where the hash table starts. We check to see if that's empty. If it is empty, we stick the things in it and reply. But if it's not, we keep looping. And if we get to the end and we haven't changed this value here, we've got this if statement to tell the user that the hash table is full. The find function just starts and hunts through it until it finds it in there. But it does use quite a simple command to do that. The multi-level index activity is reasonably straightforward. We start off by identifying the closest value in the first level table, 256, without going over. So the closest value without going over is 40, which then points to the second level table. We then identify in that second level table the closest value to 56 without going over. That is 55. It points us to the third level table then where we should see 56 directly. That then takes us to the physical location. The overflow activity describes how the system would save the record with a full hash table in a random access file. We need to explain that it can't put any hashed values anymore in the hash table, so it would go into the overflow file and store the data serially. So it would just store the data in the next available slot.